All right, so let's finish with this last topic. And so we had almost done with this discussion, but let me go back and sort of a revision for us that when we look at a gate, what we are saying is that this particular method says that the normalized delay of a gate, tau by tau naught, is equal to a intrinsic delay or a parasitic delay, P, plus a extrinsic delay. And extrinsic delay depends on two factors. One of them is what we call as the logical effort, which is a constant for a gate, defined in these terms: the input capacitance of the gate of size 1 divided by input capacitance of the inverter of size 1, and the electrical effort, which basically refers to the capacitive loading, CL by C in. CL is the load of that particular gate, and C input is the input capacitance of that particular gate, right? So these are the factors that are there. And as we saw in the last lecture, if you want to calculate the G part here, logical effort for different gates, this is the method. For an inverter, this is our 1x inverter, 4 and 8, 4 lambda, 8 lambda. Input capacitance is proportional to, S is some proportionality constant, proportional to the size here, 4 plus 8, which is 12. And so this is our CI0, the input capacitance of a inverter of size 1. And the logical factor, logical effort for this one is nothing but unity for an inverter here. CI0 gate is nothing but CI0 inverter here. Anyway, so this number we need to keep in mind, that input capacitance of 1x inverter is 12s. So when we go to a NAND 2, again NAND 2 we have to make the gate of the same size, same strength as 1x. So we make this 8 and 8, and under worst case condition each one of them remains 8. So input capacitance is proportional to 8 plus 8, 12, 16, and 16 divided by the input capacitance of an inverter, 16 by 12. So the G for this particular one is 4 by 3. And the same thing can be then used to calculate the G factor for the NOR gate here. All right, so just keep in mind that each gate you must size it to have a drive strength of 1x inverter. All right, and then look at the input and normalize it by the capacitance of a 1x gate here. So that's how you end up calculating G here. And we were looking at different examples. For example, we can apply this particular method to look at what will be the delay of this particular inverter. So when we look at a delay of any particular gate or inverter, we write it as P plus G into H. Now, parasitic delay of an inverter is 1 because everything is normalized by the intrinsic delay of an inverter. So this is 1, and G is also 1. And all we need to do is find out what is H. H for this one. And H for this one is the load capacitance of this particular inverter, CL, divided by input capacitance of this one. And input capacitance is, let's say, 1 unit, and the load capacitance is 1 plus 1, 4 units here, so 1 plus 4 equal to 5, right? So we are able to predict very quickly what would be the delay of this particular inverter. It would be 5 times the intrinsic delay of that particular inverter here. All right, same thing we had seen that, so given, so this was, and given all of these different sizes and all that, we can determine in each case what is the overall delay. So for example, if I look at this particular picture here, the delay would be made up of sum of this inverter plus this plus this plus this here, and each one of them you can see here it would be 1 plus basically this size is 2.8, so the load is 2.8, the input is 1, so 2.8 basically divided by 1. So that's the delay of the first inverter. The delay of the second inverter is 1 plus, again, the load of this one is 8. 8 divided by 2.8. 8 divided by 2.8 is how much? 2.8. So that's fine here. So it's the same thing that you need to do for all these inverters here. Just add up the delay of each one of these inverters. And all right, so this is what we were looking at last lecture here, this particular problem. So we have these arbitrary gates connected in in a chain, and what we are asked to do is determine the size of each one of these gates. Now remember, sometimes it would be given, determine the input capacitance associated with each one of these gates, Input capacitance and size are interchangeable. As you increase the size, the input capacitance changes, and they're directly proportional here. So the delay of each one of them, each one of these gates is P1 plus G1 into H1. That's the delay of the first gate. Delay of the second is P2 plus G2 into H2. Third one, and so on and so forth. Any arbitrary chain of gates, we can write it in this form. And then H1, as I said, we can write it as C2 by Cin. H1 for this one is C2, because the load of this one is C2 by Cin. The load of this one is C3, and so we write C3 by C2, and so on and so forth. So we can write the delay in this form. And to find the optimum values, optimum value of C2, we take the derivative of tau with respect to C2. To find the optimum value of C3, we take the derivative of tau with respect to C3, and with each one of them. And basically it turns out that the conditions are that Gi minus 1 Ci by Ci minus 1 is equal to Gi Ci plus 1 by Ci here. Basically what it says is that each gate should have the same effort. G1 into H1 must be equal to G2 into H2 equal to Gn into H. So that's the important result. That for optimum, for minimum delay, you should size the gates in such a way that the total effort that you see here, G1 into H1, is the same for all the gates here. So that's one of the key results here. And how do I find these? Well, we can G1 into H1 and all that you see, we can call it F, let's say, that constant F. And F is basically, if I multiply them all together, F is G into H by 1 by N. And G is G1 into G2 into all that, fine for each gates. And H is H1 into H3. It basically all these H's cancel out and you end up with CL by CL. So H is something which is known for a circuit, CL is known, input capacitance is known, so H is known, and G is, we have already seen each gate how to find G here, so G1 into G, so this is known here, and therefore you can find out what is F. And once you find out F for that particular part, note that once you find F, you can take F here, and G1 is known, so you know H1. You know H1, you know H2, and you know Hn. And from there, you find out what the sizes are. Because once you know H, the sizes are related to H here. All right? So anyway, so this is what we said. The method is find out the total, for the total part, the logical effort, multiply all the G's together, find the path electrical effort, GL by Cn. The path effort, F is equal to G into H. So this is the logical effort, this is the electrical effort, this is the path effort. And for minimum delay, F is G into H1 by N. And the minimum delay, of course, is given by this here. All right. Okay. So, and as I said, once you get F, then you basically end up getting Ci plus 1 by Ci, right? So Gi is known, and so for every stage you can get Ci plus 1 by Ci. So if you start with the last stage Ci plus 1 is known, is the load capacitance which is given. So therefore, if you apply to the last stage first, Gn into C load divided by Cn, right? So you'll get this. So you end up getting the capacitance of the last gate here, Cn. And if you know Cn, then you know the size also, right? And then you work your way backwards, and you will know the size of all the gates in that particular chain. All right, so as I said, let's come back here. So G1 is 1, G2 is 5 by 3, G3 is 4 by 3, and G4 is, inverters are all 1. And it's given here that the capacitance, when nothing is written here, it all means that the capacitance is 20 times the input capacitance of a inverter of size 1. So the multiplying factor is the input capacitance, okay? And when it's said here, it means that the input capacitance of this one is 10, which means that the size of this particular inverter is 10x. All right, so it's given here, this is 10 and this is 20. So what you need to do is H1 is, so let's say these input capacitance of this one is X. So X by 10, Y by X, Z by Y, 20 by Z here. And as I said, the method would be multiply all the G's together, 20 by 9. Multiply all the H's together, which will be nothing but the ratio 20 and 10. So it's 2. Find out N is 1, 2, 3, 4 gates in series. Find out F is equal to G, total path effort, G into H here. Then this is the effort associated with each gate, 4.4414. So this turns out to be 1.45, right? And now what you do is you start with the last gate. So for the last gate, for example, it is, so let's do that, G4. Last gate is G4, 20 by Z. G4 is the last fourth gate, 20 is the load capacitance, Z is the input capacitance, so 20 by Z is 1.45, this factor here. And G4 is 1, so we know Z here. Then you go to the next one, G3, 13.8 divided by Y is equal to 13.8 here, G3 13.8 by Y is 1.45, so you find the size of Y here, and then go forth and find X also. Okay. All right, so that's the method. Any arbitrary network of gates can be given to you, and you can find out what the sizes of Z, Y, and X or anything that's there. Now, there's an interesting application to this. For example, let's say you're given a circuit. You're given a circuit and there are N1 gates in that particular circuit, some arbitrary network of gates, and there is a CL connected to it. All right. And of course, what you're looking for is minimizing the delay. So the circuit is fixed and you're looking for minimizing the delay. And according to the method that we've just seen, you will be able to size each one of these gates and obtain a minimum delay. Now, what we are saying is, and this is the method, you'll find F is equal to G into H and all that. The delay will be sigma, whatever is Pi plus N1 into F by 1 over N1. So that's the overall delay of this particular block here. Now what we are asking is, can we introduce a chain of inverters here? Can we use a chain of inverters and obtain a lesser delay? Now this is sort of counterintuitive. In the sense, I have a circuit with certain number of gates and CL is there, and I size it in an optimum manner and I get a certain delay here. Now we are saying, can we on top of that add some inverters, add additional gates, and then obtain a delay which is less than this? In the sense that, is that possible? Normally, you're given a chain and you say, if I add additional things, well, the delay is going to go up, right? But we are saying, well, when you add these inverters here, what you get a chance is to redesign this particular one, the sizes of that one. Now you can redesign. And is it possible to get a lesser delay now? So the idea is, note that if I add an inverter, a series of inverters, how many I don't know. Let's say I add the original number of gates in the chain was N1. And I add N minus N1 inverters. So the overall number of gates in the chain becomes N, capital N. Now the total path effort, because when you add an inverter, the G of an inverter is 1. So this factor remains the same. And H, it also remains the same here. H is nothing but CL by Cn here. So H is also the same. Now note what will happen is D dash, the overall delay, will be sigma Pi, whatever were the original gates parasitic delay here, plus N minus N1. This is the parasitic delay of these inverters, plus N into F to the power 1 by N. F is the total effort to the power 1 by N. Now, if you look at this one, if you compare D dash and D, let's take the difference, D dash minus D. So you get N minus N1 plus N into F to the power 1 by N minus N1 to the power F1 by N1. So you see that there is a possibility that D dash may be less than D. I may be able to get D dash less than D. Why? Because yes, this term is increasing. This term is positive. But it may happen that this term, N into F to the power 1 by N, may be less than this. And why is it less than this? Because of this 1 by N. So even though N is larger than N1, but because it gets divided, or is F is to the power 1 by N, there's a possibility that this term may be less than this particular one. And not only that, so it's negative, and not only that, it overcomes this particular part also, and you end up getting D dash less than D. So, so what it's saying is that I can take a block of circuit and I can add a chain of inverters to it. Chain of inverters to it, so that overall, and I optimize the whole thing now. Overall, my design may be better, may have a lesser delay. Now you may say, well, this chain of inverters is what is, you can think of it, if I add an even number of inverters, it will not do anything to the logic, and basically it's like a buffer. So all that we are saying is take a block, add a buffer to it, and resize all of them in the manner that we've been talking about, and you may end up getting a smaller delay. But you'll have to do that. How many inverters should I add? You have to do it in a systematic manner here. So the issue is now, let's say D dash is sigma pi plus n minus n1 plus n into f to the power 1 by n. And now note that what is variable is n here. N is what is variable. F is fixed for the design, f is fixed, n1 is fixed, the sigma pi is fixed, and all that is under my control is n. So then, to find out what is an optimum number of n, I take the derivative with respect to n and equate it to 0. And when we do that, we get this particular condition. Simple derivative 1 plus f to the power 1 by n, n into the derivative of this part here equal to 0 here. Now I'm not going to go through the algebra, you can do it by yourself. I can define a quantity called rho equal to f 1 by n. If I define it like this equation turns out to be this one here. You can rearrange all of this and take the derivative and all that, and you can show that this equation, which needs to be satisfied for optimum design, becomes this 1 plus rho minus rho into ln rho equal to 0 here. So interestingly, this equation, it is only one variable rho, and what is very interesting is that no matter what the design, any arbitrary design, there is an optimum value of rho. There's only one value of rho for which this is equal to 0. So what I can do is I can take this function, let's say, and I can plot it. I take this function 1 plus rho minus rho into ln rho, and I plot it, and I find where does it go to 0. And it goes to 0 at rho equal to 3.55. Rho equal to 3.55. That's where this function goes to 0 here. So it starts with some positive value and then goes to some negative value. 0, it goes at this value here. All right, what does it say? It says then that n, how many inverters do I add? So not rho equal to f to the power 1 by n. So how many inverters do I add? N equal to ln f divided by ln rho. Rho is fixed 3.55, so I can take ln of that. It comes out to be 0.8 into ln f. So we get a result that given a circuit, you can add a certain number of inverters and you'll end up with an overall lesser delay, provided the total number of gates n becomes equal to 0.8 into ln f. Now, so that's an interesting result. So n1 was the original number of gates. Now if n turns out to be larger than n1, then n minus n1 number of inverters you can add to your design, and overall delay will be less here. All right, so let me show you with this example here. So n is 0.8 into ln f. To obtain minimum delay, then n minus n1 inverters should be added here. So this is the important result here. 0.8 into ln f. That's an optimum number of gates in a chain given a particular f. Right? Okay. So let's look at this one here. So I have basically a very simple problem. I have two NAND gates here, and the two NAND gates were connected to a capacitor whose size was 128 times the capacitance of a 1x gate here. Okay, and what I need to do is determine what is the minimum delay of this. These inverters are not there. Okay, initially these inverters are not there, and what I need to do is determine what is the optimum size of Y first without the inverters, and what is the delay that I get. So my original circuit has only two NAND gates. All right, so the method is multiply, find out G. So this is there, G of NAND gate is 4 by 3, this is 4 by 3, I have only two gates, so G is 4 by 3 into 4 by 3. H is 128x, and this input is 1x, so 128. So F is equal to G into H, total path effort. F to the power 1 by n, n is 2, so it's 15 for n equal to 2 without inverters. and total delay will be equal to tau P plus G into H. For a NAND gate, we normally take parasitic delay as 2. So 2 plus G into H is G into H is 15. So 2 plus 15, 17 into 2, 34. All right, so 34 is the overall delay that you get if you take this circuit with 2 NAND gates connected to a capacitive load of 128x. What is the size here? Well, size, now note that G1 into H1 is 15, G2 into H2 is 15, so we can find out H2 is 11.3, and 128 by Y, this is H2, is 11.3, so we get Y equal to 11.3. So we get a size here. Size of this particular one is 11.3. 11.3 times basically the, so you'll end up taking maybe 11 times the size of a 1x gate here. All right, so keep this number in mind, 34. With these 2 NAND gates, we have optimized the design and we have found out the optimum value is 11.3 and the optimum delay is 34. Now we are saying, can we add these inverters and improve overall? All right, so the idea is how many inverters? So again, G is same, H is same, F is equal to whatever we found. Now we use this particular result, that optimum number of gates in a chain is N approximately equal to 0.8 into ln F. So F is 27.5, so we get an answer 4.3. So it says for this kind of a path effort, optimum number of gates is 4.3. And so a buffer, what it says is 4, and 2 gates I already have. So what it says is you should attach a buffer consisting of 2 gates. 2 inverters can be added here. And F to the power 1 by N, because N, if we take 4, turns out to be 3.88. And what is the overall delay? Tau is equal to P plus GH. So let me calculate the overall delay. The first one becomes 2 plus 3.88. Second one is also 2 plus 3.88. Remember, each gate is P plus G into H. G into H is 3.88. The second one, this inverter is 1 plus 3.88, 1 plus 3.88, total delay is 21.5. So interestingly, what we have done is we've added 2 inverters to our design and overall delay has become 21.5. Overall delay has become 21.5 as compared to 34 for the previous case here. Now, okay, so the maths is telling us what is going on. Why has the delay come down? What is really going on?
Capacitance requirements within that part, the initial part.
See, this end is fixed here. This end is fixed here, right? And so think about the reasons why is this really happening? Why is this really happening? 21.5 as compared to 34. Right? So of course there's a price that you have to pay. You have to add some inverters and all that. It will take some more area. But then this is a very interesting thing that is happening, that I can add something to my circuit, re-optimize each one of them, and then end up getting a lower overall delay. Okay? All right. Now you can apply this to other cases also. And we can use G1 into HI is 3.88, and we can go back. I'll leave it for you. We can go back and determine the size here. 32.9 you will find, 8.5 here, 2.9 here, and then 1x here. So eventually, so it's not at all clear also, it's not so obvious that the size of this one is going to be larger as compared to the size of the previous one. Because previous one, if you note, previous one was, optimum size that we got was 11.3 times this one. So this was 1x and this was 11.3. This was bigger, a 2-input NAND gate, which much bigger here. So you see here 2-input NAND gate is not that big now. It's only 2.9 and this is 8.5. Of course this is pretty big, 32.9. Okay, so it's not that the area penalty is simply this much here. The size of this one has gone down. Okay, so one has to compare properly and see how much area penalty one is incurring, but there's a significant improvement in the delay here. So there are things like that you can do. So whenever, in a design, there are places where you will find that you have to drive a large interconnect. Your wires are running from one place in the chip to the other place, and there's a large interconnect. And when there's a large interconnect to be driven, or when there's a heavy capacitive load to be driven, What you do is you design buffers. So you use a chain of inverters and you design a buffer to drive that particular load. And so the issue again is, how do I design my buffer? How many inverters should be there in that particular chain such that I am able to drive that particular load with minimum delay. And so when I'm designing a buffer, again, the first inverter has a size 1 because this buffer will be connected to previous gates, it doesn't load it. All right, so size is 1, and then I have to systematically increase the size here and keep optimum number of inverters such that the delay comes out to be minimum possible here. So again, I'll so G, for how many inverters are there? G, so G is 1 here. G1 into G3 for whatever number. H is 150 by 1. F is G into H, path effort is 150. Optimum number of gates, inverters, whatever in a chain, N is 0.8 into LNF. So it turns out to be equal to 4. So I need to add 4 inverters in the chain. And so a buffer consisting of 4 inverters is optimum. F to the power 1 by N is 3.5, and then you can go back and determine what the sizes of each one are. 42.8, 12.2, 3.5, and 1. So look at the design of the buffer. The first gate is small, the second gate is 3.5, bigger, then the next one is even bigger. The ratios are 3.5. The ratio of this size to this size is 3.5. The ratio of this size to this size is 3.5. So that's how buffers are designed, with a very simple inverter, then a bigger inverter, then a bigger, then a bigger. And then you make a chain of it, and this is what will be able to drive this particular load in an optimum manner with the minimum delay. In this case is 18. So given any high capacitive load, what this is telling you is how do you design that buffer? Starting from 1x, how many inverters do you keep in a chain? And what should be the optimum sizes of that particular inverters? All right, so it's a very neat method to come up with. Now, of course, when you do simulate, it's based on approximation. It's based on that the capacitance, the H capacitances are constant. Capacitances are not constant. It's based on tau PHL, tau PLH all being the same. So many of these things are, it's not taking into account the effect of rise time and fall time on the delay. So it's an approximate method, so it's telling you how to size it. So this can be an initial design for you, and then you go ahead and simulate and all that, and then you can tweak this and tweak the sizes here and all that, and optimize it. So as a first cut at the design, this is providing you with how to go about choosing the sizes of the different gates here. All right, should I go over it, or everybody can find this out? Given an XOR gate, how do you find its logical effort? What will you do? What is the first step? Any gate that is given to you. First thing is size it such that the worst case pull down strength and pull up strength is 1x. Worst case. So in all of this, we say when you take 2 transistors in series, its strength becomes half. When there are 3 transistors in series, its strength becomes 1/3. Very simple picture here, right? So in this case, what you'll do is, this is the definition, Ci0 of gate, Y Ci0 of inverter. Both of them are of 1x strength. Okay, so then remember this is 4 and 8, and then size them accordingly, and you should obtain a, remember this one will become 8, and this will become 16. Because there are 2 of them in series, so it will become 16 and 8, 8 and 16, 24, 12, so G for this particular gate is 2. So a calculation of this is basic. Given any particular gate, we should be able to calculate what the G value is. And the rest, of course. The next thing is, of course, given now, how do I, given any circuit, how do I predict what the delay is going to be? Right? How do I predict what the delay is going to be? Our basic equation is this, P plus G into H. P for inverter is taken as 1. For other gates, we'll give you what the parasitic delay is. P for a NAND gate will give you 2, NOR gate also maybe 2.5, and like that, the values for P would be given to you. So P for a gate will be given to you, G you have to know, and H is given in the problem. H is you have to deduce from the problem here, right? So the first gate, if everything is given, first gate, first inverter's delay is 1 plus 4. 4 is, remember what is H? The input capacitance, the load capacitance divided by input capacitance. So it's 5, delay of the second one, please note 1 plus 12 by 4 is 4, and delay of the last one is 1 plus 64 by 12, 6.33. Now, given when you see something like this, is the design optimum? Now, one of the things that we know in an optimum design, the delay burden is shared. So in an optimum design, what you will end up getting is that the delay of the first gate or the last gate, the second last, and all, they will all come out to be the same. And when you see 6.33 and you see 4 and 5, it's not optimum. And obviously, you know, to find the optimum, you have to take G and H, and we've said 1/3, and you find the effort here, F4, and then you size it properly here. This becomes 16, and this one here. So these are relatively straightforward what we have discussed. The trouble or the interesting things come when you see something of this sort. It's not a straightforward linear chain. It's not a straightforward linear chain. So what do we do in this case? So in this case, the straightforward formula doesn't apply. The formula was, remember, for a simple chain. Now here we have branches. And the branches, there is one inverter which is given as 4. So you have to go back to the basics. Tau is 1 plus x2. Inverter, 1 plus x2. x2 is the load, and here. Tau 2, please note tau 2 would be 1 plus x3 is the size here, so the gate x3 is here, plus 4. The total load of x2 is x3 plus 4 and divided by the input capacitance here, so x2. And then the tau 3 will be equal to 1 parasitic delay, 64 by x3. So now the goal is overall delay, so you have tau equal to sum them up, and you have to find out the optimum value of x2 and x3. So again we take the derivatives, del tau by x2 equal to 1, you get some equation, del tau by x3 equal to 1, you get some equation.
Tau 64 by x3 plus 4 or x?
No, the input of that particular gate, that's it. The input of this particular gate, input capacitance of this gate. So 64 by x3. This is the total load capacitance of this particular gate, which is x3 plus 4 divided by the input capacitance here, which is x2. So now, if my circuit does not fall into a simple chain, then you go back to the basics. You write down your tau 1, you write down your tau 2, you write down your tau 3, add them up. What is the optimum? Take the derivatives, equate it to 0, you'll get some equations, solve them up. In this case, the equations are slightly complicated. You get a value of 4.88 and x2 is equal to 3. Okay, so you end up getting what the optimum sizes are. All right, so that's what I'm saying. So in some cases simple, in some cases things may be. Another case is here. Look at this circuit. Determine the optimum sizes for y and z. So it's now it is given here. This is one size 1. The size of both these NAND gates are the same, y, and the sizes of all these NAND gates are the same, which is z. And each one of them is loaded with whatever here. And what we need to do is determine the size of z and y. All right, so how do we do that? What is the starting point? Let's go over the steps. What is the starting point? Write down the delay expression for each one. This one, and this one. Write it down. Tau 1, is that clear? P, parasitic delay. Whatever parasitic delay is given in the question, use that, P. What is this? The G value for a NAND gate which is fixed. For a 2-input NAND, now remember, for a 2-input NAND gate it is fixed. For a 3-input NAND gate it would be something else. Okay, so it's not given here. Actually, it should have been specified that each one of them is a 2-input NAND gate. So it's 4 by 3, and the net capacitive load is 2y, y plus y, 2y, and the input is 1, so 2 by over 1.
See, the net capacitive load is 2y. Had there been 2 inverters in place of the 2 NAND gates for y?
2 inverters in place of?
These 2 NAND gates.
Okay.
So because the capacitance at that node would be different for an AND gate.
No, so we are saying size. So when everything is multiplied by the capacitance of an inverter of size 1. So everything specified like that.
So this is YX NAND gate.
No, Y has got nothing to do with NAND gate now. We are saying the capacitance of this is Y times the input capacitance of the 1x inverter. That's it. And once you find the 1x inverter, then you know what the size of the NAND gates are. Okay, so everything is specified in that terms. Because the ratios that we are taking are the ratios of the capacitors. Okay, so 2y by 1, tau 2, look at it here, would be, we are focusing on this. Let's say we optimize this particular chain here. Okay, so tau 2, this particular one is P, parasitic delay, 4 by 3, and its load is 3z by y. And then tau 3 is equal to P plus 4 by 3, 9c by z here. Right, so now you have all of these, add them up here. So now what do we do? We have all these delays. What do we do? Add them up. Will you go ahead and do all the derivatives and do all of that, or it's very easy to cast it in a different form? See, we have the result for what? See, if I take this and write it in this form, P plus 8 by 3 into y by 1, we write it as P plus 12 by 3 into z by y, and we write it, this is in the same form. Now, this result is in the form which was there earlier, except that we interpret this as G1, we interpret this as G2, and we interpret this as G3. Right? And then we don't have to take all the derivatives and everything, and you go back and use the same F equal to G into H1 by 3 and all that, and use that particular form. Okay? So internally, of course, what do you take as, you call this as G, and then this becomes Y by 1, this becomes standard form Z by Y, and this becomes 9 by Z. And so you use all the results, and then from there you try and figure this out, what the values are for optimum values are. Z is 2.5 and 2.4 and Y is 1.92. Okay, so given any network, these are our starting points. If it's a simple problem, then you can straight away use the expressions and all that and calculate. If it's slightly off, then you have to write it down. Maybe you can still cast it in this particular form. If not, go back to the basics, take the derivatives and calculate what the optimum values are.